Guys, let's start, please. So, it's a great pleasure to have Stephen Wolfram here visiting us and UFRJ. I think many of you know Stephen from Mathematica, which many of us use in our day-to-day research or studies. And of course, Stephen was first started as a physicist, so he was a very early, physicist, very early physicist career. I think your first paper, I think you were 16 or something. 15. So you have a PhD by 20, am I right? Around 20?
Yeah, PhD.
And he was in Caltech, Princeton, and Urbana-Champaign, and now he's, of course, founded his own company, Wolfram Research, which has developed Mathematica, Wolfram Alpha, and I'm sure he has more stuff up his sleeves that we'll try to extract a little bit today. And I will leave the floor to Stephen. I don't want to make a long introduction, so please, Stephen, thank you.
Thank you very much. All right, so I want to talk a bit about tools that I've built for computation and also the promise of computation as an idea itself. So first of all, maybe actually I'm curious, who here has used Wolfram? Great, hey, wait a minute, I should take a picture. It's good for the team. Let me do that again. I'm going to ask you again. That's great. Thank you. Okay, so Wolfram Alpha is kind of our drive-by, kind of quick computation version of the things we've tried to build. Kind of the way Wolfram Alpha gets used by, for example, students and so on, tends to be for doing mathematical kinds of things. You can say, what's the integral of x squared, tan x or something. Let's see, do I have to make this? Maybe this is difficult. You see, I type these things in at random, and then I realize that actually x squared tan x is not such an easy integral to do. It's what I get. Okay, it involves a trilogarithm function. Those are okay. Let's try a different one. The impressive thing is that it could do that one. So okay, this is one that I long ago stopped doing integrals by hand. Probably I haven't done one by hand for 35 years. So I don't. But anyway, so the thing people often end up using is the step-by-step solution mechanism. It's worth realizing that the step-by-step solution that Wolfram Alpha is giving you has nothing to do with the way that Wolfram Alpha internally computed the answer. It's purely made for human consumption. Yes, definitely. Why is this not working? This is suspicious. I thought we had a wonderful network connection here. Okay, you know what? I'm going to let's. Anyway, the thing that maybe you're less familiar with. So Wolfram Alpha powers things like the Siri intelligent assistant from Apple and a bunch of other things like that, and it powers them by providing knowledge about the world. Why is this not working? This is very disturbing. Okay, there we go. This should be almost instantaneous, and this was so this is a typical example of kind of a question about the world that we can ask Wolfram Alpha. It's ISS. It will tell us some interesting facts about the International Space Station, like it tells us that's where the International Space Station is right now, things about its velocity and so on. And so what's happening here, there are really three components to Wolfram Alpha. One is natural language understanding, trying to understand what the question meant. The second is trying to actually use curated knowledge about the world. And the third is computing things from that underlying knowledge. So in this case, there is some data that comes in from a feed that tells us the orbital elements for everything that's orbiting around the Earth. But given those orbital elements, we actually have to solve physics equations to work out where the ISS is right now and to generate this report. But we can ask something like, what is the population of there we're using natural language understanding to understand that question. Why is it so slow? Oh, it's driving me crazy. so fast, moments ago. But, come on, this should be absolutely instantaneous. What should I do? I'll just try it again. It's, for some reason, it's now. We may want to switch to using Chrome.
Everyone is using the Wi-Fi.
Yeah, well, I was wondering. Yeah, right. If everybody is wondering, that's why I have to give an exciting talk, because then you won't use Wi-Fi. But okay, so that's so if we could say something like, what's the population of I'll spell it that way. That doesn't look right. Is that right? That's spelled wrong. SIO. Okay. Oh, great. Correct. Okay. So anyway, the goal here is to understand natural language in the kind of way that people will ask these questions, and then to be able to answer the questions. So ultimately, the way that works is that we're translating that natural language into an internal symbolic representation from which we can actually do these computations. And that internal symbolic representation is this thing we call Wolfram language, which is the language that is now what Mathematica has turned into, and it's the language which is kind of the base for all the technology we're building. So I can go and just directly start using Wolfram language, and this is just a notebook that you can, okay, 2 plus 2 is 4, great, we can do the standard kind of computation, okay. Now, the point of Wolfram language is to be able to represent and compute with any kind of thing you might want to compute with. So, for instance, maybe a good place to start. Let's do a computation with a graph. So we can generate some graph, and here's a graph, and now we can do all kinds of computations with this graph. So, for example, we could say, what are the communities within that graph? We can compute. We could render the graph. I don't know. Let's do something different here. Let's take that graph and let's render it in 3D. Let's try that. That's a nasty random graph, so it's kind of doesn't render that beautifully in 3D. But so we can do we can deal with all different types of computation. So, for instance, let's do let's do an image here to start with. Let's pick up an image from the camera. There's an image. Okay. So now I can do computations on that image. So I could, for example, say, edge detect that image. I could even say dynamically edge detect the current image. So now we'll generate something where, as I move around, it will do the edge detection. Or I could do something like, I could say, here, let's do this. Let's try taking that image and let's nest edge detection for that image. So let's do sort of 5 levels of nested edge detection. And maybe we can just, for fun, let's try and make a 3D image out of those. So I think we can stack those up. I should try this. Okay. So we just stacked up those. It wasn't very exciting, so we can have that many levels, but this. Okay, so there we go. So now that's a 3D image made from stacking those levels. And we can do image processing on that 3D image and so on as well. Or we could do, I don't know, let's try another kind of thing. Let's do this. How about we capture some audio? Hello. Okay, let's see where that should come back as an audio object. Now, for example, I can say, show me a spectrogram of that audio object, and there's the spectrogram. And I could, for example, say, if I want to, let's do something weird. I'm not sure, I may have to plug in. I'm not sure if we have the sound set up there. But I could do all kinds of audio processing on this and make it come back in all sorts of different ways. But sort of the big idea idea here is to be able to compute on all kinds of different things. And so, for instance, well, let's take another example. Let's do some computation with words. So, for example, if I say, give me a word list, okay, it's set. I've set my computer to produce Portuguese output, which is not useful for me, but perhaps it's useful for you. So there's a list of words in Portuguese. Now, for example, we could say, let's do this. Let's make a histogram of the string lengths of words in Portuguese. So there it is. And we could, for example, we could take a word cloud. We could just take what are the first letters of all those words. They were on line 15. First letters of all those words, and now let's make a word cloud of those first letters. Find out what the most common sort of first letter, what the thickest section of the dictionary should be in Portuguese. Is that right? Is that plausible? Anyway, so this is so we're kind of dealing with different kinds of computation. We can deal with all sorts of sophisticated mathematical computation. For example, let's take what could we do here? We could take some. Well, here let me do this. Let me make a random collection of points. Let's take a random real number in the range, let's say -10 to 10, and let's make 100 points, 100 triplets. Okay, so those are like points in 3D space. Now I could say something like make a mesh around those 3D points. So now this is an object that makes a mesh around those points. And so now, for example, I could pick up that object and I could say, what's the volume of that object? So that volume of that object. So now it will tell me. So it's now computing the computational geometry to work out the volume of that object. Maybe I can do something slightly more elaborate. But let's for example, let's say we want to make a plot of the distance between the point, that object, and the point 0, 0, z. For z running from, let's say, -20 to 20. So this should now, is that right? Let's see, okay, that wasn't that exciting, but anyway, you can see what's interesting is that you can kind of mix this geometric structure with computing distances, with plotting things, and so on. That's kind of the goal of our language is to be able to combine all these different kinds of operations together. So the next big thing about our language is that it knows about the real world, so to speak. It's not just something that's dealing with things. It has a huge knowledge base built in. So, for instance, let's go back here. We can actually just deal with the city of Rio de Janeiro. Okay, there it is. We could say, for example, show me. Let's do this. Let's just say make a geodisc around the center of Rio de Janeiro of, let's say, make a 10-kilometer disk around the center, and now show us graphics that this requires again. Oh, there we go. Okay. So there's a 10-kilometer disk around Rio de Janeiro. We could, for example, say if we want to, let's do this. I'm curious what this is like. Instead of this, let's go and pick up the geo-elevation data. Since I've noticed that this is a very rather mountainous place, let's see if we can get the geo-elevation data for the city. Oh my gosh, what happened here? Okay, so let's say now we say, for example, we can just take that data and we can try and plot it. So plot it like this. Let's say we want to. I think there might be some peaks, so let's say plot range for all. And so now this should be taking that geo-elevation data and making. There we go. Wow, that's pretty mountainous. Okay, and looks like there's a contour there, which is probably the coastline. So this is again, this is the kind of thing. So now, for example, one thing we could do, take this, and if I wanted to, I could make a histogram of kind of the heights of things in this region and so on. Or I could take this and I could do essentially 3D image processing on it. You take So that's the kind of thing that that's possible there. So we can deal with, in addition to, we know lots of things. Let's go back to Rio de Janeiro. But actually, let's do it for Brazil as a whole. Let's say we can say for Brazil. Let's just ask for the population of Brazil. Okay, and that's now using natural language to ask that question. When we hit control equals, you do that, and eventually you'll get back this thing which shows us effectively the code that can be run to get that answer. And if we wanted to, we could, for example, change that code. Oops, I should have differently here. We can change that code. We can change that to say, give us the result for all the dates that you know about. So this is giving us. Looks like it's actually giving a projection as well. So this is giving us the population of Brazil from 1600 to the future here. I think probably this log plot. I bet on the log plot we'd be able to see more about what's going on. Okay, so there we go. So in any case, this kind of idea of having lots of knowledge about the world is. Let's try another thing. Let's try something like this. Capital cities in South America. Okay, so there again, we're using natural language here. Now that will resolve into a symbolic query. Then we get the result. Now, for example, we can say what are the geopositions of those cities, and hopefully, connected network, one network. This is very inconsistent because sometimes it's coming back super quickly and sometimes it's freezing. Well, in any case, this. Let's try. It seemed to work, and I just tried it again. Or maybe it will fail perfectly this time. Come on. Okay, well, I'm trying to get it to tell me the geopositions of those cities, because then we can do all kinds of neat tricks, like work out a shortest traveling salesman tour around the cities and so on. Why is the network frozen? Let us see whether the network, whether everything about it is frozen. It's pretty slow. It probably already cached all of that page. Okay, let me try. Let's actually get very explicit here. Let's say ping time. Let's see whether it will ping successfully. This is not looking good. This should be like a 200 millisecond ping time. Okay. Well, that is answering. That's answering the question. Well, okay. In any case, but let's go on and look at some other things which hopefully we can do locally without having to connect to the outside world. Let's go back to that image I had back there, and let's try and do some machine learning kinds of things on this image. So that's another big area for us in recent times with machine learning. So we can take that image, and I can say image identifier. I hope this doesn't have to connect to the network. And we can say image identify that picture. And okay, great. It says it's a person. And I can do kind of a. Let's see if this works. I could again. I hope this won't have to connect to the network because sometimes it will. If I don't have this particular classifier cached on my computer, it may have to go to the network to get it. Okay, so then. Okay. So one question you might ask is, how does this actually work? And we can actually see we have now a neural net repository that contains lots of neural nets, including, for example, the neural net that we use for image identification. So that neural net was trained on around 30 million images with about 10,000 kinds of things. This is the network, and you can drill down and you can see all the features of the network. And if we feed this, for example, let's feed this picture to that network, and we'll probably go and say person. If we're curious what's happening inside that network, we can say, let's just take 10 levels inside the network and find out the intermediate result that we get. So maybe we can just say image of that, and now we'll get all of the pieces that were part of the internal analysis done on that picture by the network. sense of this, maybe we can say feature space plot. So this will try and take those images and kind of arrange them in some kind of feature space to show us what the different aspects of different kinds of pictures that are there are. So actually, if we just say, to try and understand how this works, let's just say we just take letters of the alphabet and we just take images of letters of the alphabet. Okay? And now we could say something like feature space plot of those, and now we'll see that letters that are visually similar, like V and Y, appear nearby in this feature space plot. And that's kind of the essence of what's happening in a lot of machine learning kinds of applications, is you're trying to sort of find a feature space in which you can identify what's close to what. Now actually, our machine learning stack is kind of the most automated machine learning stack that people have built. And it's been really interesting. I just saw, actually this morning, I just saw a new application of that. Some physicists using it to study results from scattering and Schrodinger equation. And the very amusing fact was that when they peeled apart the neural net that they got, it was a neural net representative of the language, when they peeled it apart and they looked at what it had learned as it was trying to study scattering and the Schrodinger equation, it was actually apparently learning the orders of perturbation theory that physicists have also identified. So it was kind of relearning how physicists have learned how to do computations about that kind of thing, but it was happening automatically within this neural network. Actually, we can just look at what's happened. You just look at what it's like to train one of these neural nets. So for example, let's get some training data. So this is, oh come on, this may have to connect to the network. Okay. So this is kind of a standard training set, the MNIST training set of handwritten digits. And these are kind of just examples, like here are a bunch of examples of handwritten zeros. It says it's 0 in each case. So let's take a sample of this. Let's say we take a random sample of 2,000 of those. And okay, now we say for this, we might just say, give us a classifier that will classify any input according to what digit it corresponds to. So now it's kind of learning what the learning how this classifier should be set up. We've now got a classifier. Now if we feed it one of these digits, it should tell us what it is. So we just taught this particular machine learning system that result. If we wanted to, we could do this with, we could just pick our neural net. Let's say we can go to the model neural net repository. Let's pick one of the very old, pick this, let's say uninitialized evaluation net. So this is the untrained version of a very simple network. There's just a 11-layer network. And if we just say net initialize this, so that we set it up with random weights, we can take that, we can say, okay, let's do that. Now this is with random weights, so this will just give a totally random answer. But what we can do is we can say net train of that randomly initialized network using the actual data that we have there on line 46. And now it'll do training, so now you'll see that it's measuring the error rate as it tries to optimize the network to learn, in the best possible way, learn this way of reading handwritten digits. And it will eventually, we'll probably stop it partway through, it will give us a network, and if we now want to use that network, we just take that network and use it on this, use it on this, and we'll give us a result. So that's kind of what it looks like to train a neural net. You could do much bigger training on big parallel GPU farms and things, but this is just the kind of the local version just training on my computer. So, it's interesting to see all the different kinds of, let's go back and let's see if the network is alive again. I can show you some different kinds of data that we can deal with. So let's pick another kind of, let's take, let's pick anatomy, for example. So let's say we've got a left hand, let's see if this works. Oh, come on. You know what, I have a feeling I'm going to switch. Oh, now it works. Who knows? Okay. Well, let's see, this requires it loading a bit is now going to take the, so this is now a 3D representation of the various systems in anatomy of the hand. And so it's kind of interesting. You can pull out each bone, you can start solving differential equations on the geometry of that bone. You can do all kinds of things like that. There's just a lot of different kinds of data that we're dealing with, whether it's data about chemistry or about movies or about, I don't know, let's try taking, let's do this. Let's say we take random entity, movie, let us pick, I don't know, 20 random movies. Okay, so assuming we're connected to the network, there we go. So we've got 20 random movies. I have no idea what any of these are about, but we can say, let's try taking, these may be horrific movies like that. We could ask it the ratings and so on for these movies. We could also ask it the box office success of these movies. But here, this works. This is just going to download movie posters for these movies. Oh, there we go. Okay. All right, so that's some of those movie posters we can have, but if I say delete missing here, actually one thing I can do, let me use feature space block. Let me just use feature space block here. And now it'll arrange those movie posters, or back and forth, probably. It kind of arranged those movie posters by the style of the movie poster, or we can say, that's like, so we can say chromaticity block 3D. We can say, take those movie posters and show the colors in the movie posters arranged in 3D color space. So that's we can start doing some analysis of the correlation between the type of movie and the colors of the movie poster, things like that. So there's lots of kinds of data about the world. Here's another kind of thing. I mean, we can say something like, let's pick something like Mexican-American War. So this is a very different kind of data. And we could say, for example, what were the battles that occurred in that war? And we could probably get those. And then maybe we can say, make a geoplot of where those battles were. And then we can start doing, we could probably do that by time, and we could do all kinds of other things. So this is, again, these are examples of data. And what we've been doing for the last, basically for 30 years, but intensely for the last 15 years, is kind of ingesting all sorts of data and curating it and setting it up so that that data can be computable, so you can actually expect to use it in a systematic way to do computations. So this is kind of the types of things. I mean, so in Wolfram language, we have lots of different kinds of areas that we cover. Let me show you another thing, perhaps is of interest about this. So everything I've been doing right now, I've been doing just on my desktop computer in a local notebook. But you can also do things in the cloud. So if I take, let's say I just create some random plot. Let's say I do something like this. Okay, so here's a sort of simple plot that I can manipulate. Now I can say cloud publish that. And so what will happen is this will now create a web page where I have where I have an active version of this thing, and this is just running through a web browser. So it takes a little longer to do each computation because it has to go back to the server in the cloud to compute the result, but you can still do the same kind of thing. And in fact, you can also go ahead and just use the cloud version of whoops. So this is now just running through a web browser, and I can now do any of the kinds of computations that I was doing there. I could say, for example, I don't know, let's make 40 random colors, for example. So I can just do that computation, and this is now a notebook, just like the notebook that I had. So I can say, here is a heading, etc., etc., etc. I can do all of that just directly in the cloud. And this was a big effort of software engineering to make all of this work. could say, let me try and create an app. So let's say I make a form page that will take a location. Let's try just making a, let's just make a picture of a, let's say a 1 kilometer, let's do something similar to what I did before here. Let's just make a 1 kilometer location, diameter image. Okay, so now I can do this, and I can just say cloud publish that. So now this is saying I'm going to make a form where it's going to ask for a location, and then it's going to compute that geographics thing. So let's say the location, it might be Eiffel Tower. That this web form can make use of our natural language understanding capabilities to figure out, okay, what's the Eiffel Tower? Okay, there's the graphics from the Eiffel Tower. Maybe I could say something else here, and I'll get the result. I can also make this, if I'm trying to build this into a sort of big software engineering system, I can say this is an API function. So now I'll get something here which can be used as an API that I embed in another program. So for example, I might say, give me the Java embed code for that API. So then I've got a piece of Java code which will call that piece of Wolfram language code in the cloud, execute and get the results of that. So okay, so that's sort of an outline of what Wolfram language, the kinds of things Wolfram language does. I mean, the way I see what we're doing from a practical point of view is there's sort of these layers of computation ability that people have had available in practical computing. I mean, back 60 years ago when digital computers were new, there was, people were just given raw computers, which you programmed in machine code or something. Then, early languages like Fortran and so on came along. Then later operating systems, then user interfaces, networking, and so on. And as time has gone by, there kind of are more and more layers of sort of computational ability that one is able to take for granted in using computers. And what we're trying to do is to add sort of a layer of computational intelligence that people can just take for granted when they use computers. So you don't have to be, you can just assume that any computer that you walk up to will immediately know what the geo-elevation data for the city you live in is, or what the weather was like, 30 years ago in wherever you live, and so on. So that's kind of the goal here. Maybe I can talk just a little bit about the kind of broader sort of philosophical implications or something of what we're trying to do here. This is part of kind of talk a little bit about computation as an idea. So I've been interested a lot in using computation as a way to model the world, and sort of trying to turn everything we know about into something that can be represented computationally. So for example, at a science level, I'm not going to go into this in tremendous detail here, although I'm happy to answer all kinds of questions about it if people are interested. From a science point of view, I've sort of been interested for a long time in how we build the most general possible models of the world. And people have, for the last 300 years, people kind of have treated mathematical equations as kind of a gold standard for making models of things. I got interested years ago in how you sort of generalize that notion, and I realized that you can use programs as kind of a generalization of how you can represent rules about how the world works. So then I got interested in, if you just think about the universe of all possible programs, what kinds of behaviors are out there in that universe of all possible programs? And I particularly got interested in studying the simplest programs one can imagine. So a particular class of those that I studied a lot are these things called cellular automata, which are just a line of cells, each one is black or white, and then there's just a rule that says how you update those colors in a succession of steps going down the page. So in a very simple case, this is what you might get. So that's that particular rule, and I might run it for 30 steps, and this is what it does. You start off with a single black cell, and it makes a trivial pattern. But what's interesting is if you change this rule a bit, just change then run it again, now you get a more complicated pattern. Actually, that pattern, if you run it a while, you'll just see it makes a nice nested pattern. So, okay, so you might have thought, okay, if you have a sufficiently simple rule, then the behavior that you must get out must be somehow correspondingly simple, or somehow have some kind of regularity that reflects the simplicity of the rule. But then you can do an experiment, and doing computer experiments is a wonderful methodology in whether you're doing mathematics or you're doing all kinds of different things. It's a methodology that Wolfram language kind of really makes easy. And so let's say, for example, here, let's just make a table. Let's make a table of a whole succession of different rules that operate in the same way. So we're just starting off from one black cell in each case. In many cases, the result is totally boring, but there's a couple of nested ones, and there is my all-time favorite science discovery. It's rule 30 in the sequence of these rules, and that's what it does. So you might say, well, if we just run it longer, maybe it will resolve into something simpler. So let's try that. Let's just get here. Here, and run rule 30, let's say for 300 steps. Okay, so that's the result of this. So this is, at some level, just totally weird. Because, the rule that made this is something extremely simple. And, you might say, based on sort of standard intuition, you might say, oh, if the rule is that simple, it's going to make some behavior. The behavior it's going to show is somehow correspondingly simple. But that's just not true. And this was sort of a fundamental discovery, I guess, that I made in the early 80s that led me to a whole new kind of science. I wrote this big book called A New Kind of Science about the implications of basically this discovery that in the computational universe of all possible programs, even when the programs are simple, the behavior can be really complicated. So there are many kind of basic sort of scientific conclusions from this. Among them, when you see complexity in nature, this is sort of, I think, the essence of the origin of a lot of complexity that we see in nature. But there are also some general principles that emerge. One of the ones that I think is sort of the most general is a thing I call the principle of computational equivalence. So you can think of what this system is doing as being like a computation. It's taking its initial data, it's computing what the result is going to be. But the question is, how sophisticated is that computation? And you might have assumed that when the rules are sufficiently simple, the computation that's going on must be somehow correspondingly simple. But what this principle of computational equivalence says is that above some very low threshold, actually, essentially any system whose behavior is not obviously simple will be doing a computation of sort of maximal sophistication. So, okay, well, what does that mean? Well, among other things, that means if we that we should be able to make an arbitrary computer out of one of these systems. So let me show you an example of another one. This is rule 110. Actually, let me do it with random initial conditions here. So let me just say that. So this is here. I'll make a bigger version of this. So this is something where you can see it starts off with a sort of random initial condition, then it has all these kind of particle-like things running around. If you're into particle physics, for example, you can kind of study these a little bit like the way you study particle physics with all kinds of different interactions between them and so on. And one of the things that we know is true about this rule 110 cellular automaton is that you can arrange those particles in such a way that you can make them sort of implement any Boolean function or actually do any computation that you specify. So that means that we know that even though the rule for this is incredibly simple, this thing can do any computation you want. And this is kind of evidence for this principle of computational equivalence, that the system, even though it has very simple rules, it can do universal computation. It can do an arbitrary computation. And we found a bunch of other examples of things like that. There are many implications of the principle of computational equivalence. One of them is a phenomenon I call computational irreducibility. The question is, if you're trying to work out what happens after a certain number of steps in this pattern, one way you can do that is just run the rule and see what happens. Another thing is you might imagine you can kind of just use some very smart mathematical method and kind of just jump ahead and get kind of an exact formula for what goes on. But the principle of computational equivalence kind of tells you that isn't going to work, because your smart formula for what's going to go on is itself a computation, maybe implemented in your computer or your brain or something, but it's a computation that is just equivalent to the computation that's going on right here in this system itself. And so the fact that those computations are equivalent means you can't expect that one can outrun the other. And so you're kind of forced to realize that there's this notion of computational irreducibility. It's kind of a limit to the predictability that can exist for systems. So that has all kinds of consequences in all kinds of different areas. Actually, from a philosophical point of view, this principle of computational equivalence is what led me to develop Wolfram Alpha. I mean, since I was a kid, I'd been interested in kind of, can you collect knowledge in the world and make it automatic to answer questions from it? And I kind of assumed that to do that, you'd have to build kind of a brain-like AI that would have some magic intelligence feature that would let it do that. And then when I studied this sort of basic science, I realized that actually, according to this principle of computational equivalence, at least, there's nothing uniquely special about something like human intelligence. It's just another computation that's equivalent to all these other computations that all sorts of systems can do. And so the result of that is that I sort of realized, actually, you should be able to do something like Wolfram Alpha just using computation. And so then I started doing this project, and it turned out, yes, it was actually possible. It wasn't clear that the project was being tried in the right century, so to speak. But people had tried to do similar things for probably 40 years, 50 years before Wolfram Alpha, and always failed. The reason that they weren't able to do it in the end was probably because they didn't, it's a pretty big project, and ingesting sort of all of this knowledge is something that's just a hard piece of engineering, but it's also that you need this target language, this target symbolic language, to be able to actually represent things in the world in a way that you can compute from them. Well, there's all kinds of different things to say about, let me talk a little bit about sort of the computational universe and what's out there in the computational universe and how we use it. So the computational universe is full of all kinds of programs like this. One of the the most ambitious basic science question about the computational universe is our physical universe out there somewhere in the computational universe? Is there some way of going underneath kind of our existing ideas of space and time and so on, and making a sort of ultimate model for physics based on these kinds of ideas? And I think the answer is, well, I don't know what the answer is, but the answer is it's not obviously hopeless. And I've actually managed to get fairly far in doing that. I mean, the way that I particularly tried to do it is sort of my favorite representation for sort of what's underneath space-time is some kind of network where all that you have is sort of connectivity information about the nodes that exist in the universe. And then the question is, can you, so how does that thing sort of evolve? And so there you can, just like you can enumerate cellular automata, like I was showing you, you can enumerate possible rules for updating the network. And so there are all sorts of different things that happen, like this one here is definitely not our universe, because absolutely nothing ever happens. So some of these, the most interesting thing one can say, well, every time one can sort of see what's going on, we can say, no, that's not our universe. Because as soon as we can see what's going on and analyze it in some straightforward mathematical way, it's not rich enough to be our universe. But there are examples here of even in the first few thousand of these candidate universes where the behavior is complicated enough that you can't say for certain that it's not our universe. So how does this network end up turning into our universe? Well, the main point is that the limit of this network, when it gets very big, it's like asking for the limit of molecular dynamics. You have a bunch of molecules bouncing around, and in the limit, they can behave like a fluid, like a liquid, like water or something, that acts like a continuous kind of fluid. It's in the same way that this kind of model of space-time can act like continuum space-time on a large enough scale. Now, there are many technical details. For example, this is a pure model for space. There's no matter basically has to emerge as a feature of space. So, for example, remember that Rule 110 cellular automaton, where every cell acted the same, yet you could see those particle-like things running around inside it. The same kind of thing has to happen in this model of the universe as a network and so on. And actually, we have some cases where we can see particle-like things in this network. They're kind of like topologically stable excitations that one's used to from condensed matter theory that applied in this kind of network context. And I guess the big result from about nearly 20 years ago now about these networks is that I found that for a large class of underlying dynamics of these networks, the limiting behavior when the network gets very big, just like you can work out when you have a bunch of molecules bouncing around, that the limiting behavior of the continuum fluid satisfies certain differential equations like Navier-Stokes equations. So similarly here, it turns out that the limiting equations that the manifold that emerges from the sort of large-scale structure of this network turns out to be the Einstein equations, which are the equations that we believe work for gravity in the physics that we know. So that's kind of exciting. And one can go on and one can see at least certain features of quantum field theory, although to get all of quantum field theory is a different challenge. But anyway, so that's one of the things that might be out there in the computational universe is our actual universe. Another thing that's out there is just a huge amount of technology that one can mine. So for example, this Rule 30 cellular automaton, we've used this for a long time to generate random numbers because the center column here is a really good source of randomness. And you can go and you can search this computational universe for programs that are useful for all kinds of different technological purposes. And in general, there's kind of this picture of sort of computation and the computational universe as this huge supply of different capabilities. And in fact, when those capabilities are kind of used by nature, used by the universe to do things, they're capabilities that we can potentially use for particular technological purposes. And really the big challenge, I suppose, is there's this sort of infinite collection of capabilities in the computational universe. There's the things we think about and want to do, and there's the question of kind of making a bridge between those two things. And I see that as being the role of Wolfram language is this kind of computational communication language that allows us as humans to express things that we want to do and then get them kind of executed in this computational universe of possible programs. And there are many sort of implications of that idea. It's kind of like when we think about AI, we're kind of what we have to realize is the part of, we can automate many, many things, but what we can't automate is figuring out what we actually want to get done. But we have to have a way to express what we want to get done, and that's where Wolfram language comes in as a way to precisely express what we want to get done. And the notion is, this is that we're kind of taking our thoughts and casting them into kind of a computational form that we can then communicate in the easiest possible way to a computer. Actually, one of the things that I've been interested in recently is kind of the problem of education. And it's, if you look at the future of what people will do, for sort of any field X, from kind of archaeology to zoology, there either is now a computational X or there will be soon. And so the question is, how do people learn how to do computational X for all X? And what's really involved, in all cases, it's kind of the same story. It's a basic skill. It's kind of the skill of doing computational thinking. Computational thinking is not the same thing as like writing, low-level computer code. In fact, if you look at sort of the education process, people occasionally say, oh, we should teach coding, which usually means writing low-level code with loops and variables and procedures and all this kind of thing. This is, our efforts with Wolfram language are to basically automate away all of those details. You don't need to be writing detailed loops and so on. You're just using things that relate directly to the kinds of ways that you think about the kinds of computations you want to do. But the skill that is relevant is to formulate your thoughts in a kind of clear enough way that you can communicate them to a sort of smart enough computer. We're trying to provide the smart enough computer, but what people have to learn is kind of how to formulate their thoughts in this kind of computational way. And one of the things that has come out for a sort of educational level, it's great to present things in kind of computational essays. So, this notebook, for instance, I could add a bunch of text to it and so on, and I can explain what I'm talking about in a mixture of human language and computer language. And the computer language is something that can be read by the computer, but it can also be read by other humans. It's kind of like a generalization of things like mathematical notation. It's kind of a precise way to represent a certain kind of thinking. Actually, I've been having fun kind of trying to see just how young you can, what age of kids can really learn this well. I mean, I wrote a book, or we have a thing. I wrote this little book that is basically a book for kids about our language that kind of assumes no knowledge of computers or of math or anything like that, and tries to introduce the language. And it turns out it seems to work down to about age 10 or 11. So by age 10 or 11, people are able to, it takes about 20 hours of exposure, at least for fairly bright kids, to get to the point where they're fluent enough that they can take sort of an idea that they have and turn it into Wolfram language code and see what happens. Now actually this works not only for kids, it works for lots of other people too. And one of the interesting things that's been happening is, I've talked about sort of computational X for all X. There's a lot of areas of academia, for example, that have traditionally not had any kind of computational or quantitative component are suddenly able to have that component. So, a humanities area, a history department, something, all sorts of different areas where there hasn't really been, where there hasn't been sort of a systematic kind of computational way to deal with them. That's now becoming possible, and with our language, we're providing kind of the tools to enable sort of computational X, but for all X. And I think this process of learning computational thinking, I think this is the most important skill, the single most important skill, more important than learning all kinds of mathematical skills and so on. It's the single most important skill that people should be learning and should be incorporating into the work that they do, but in particular that people should be learning in the sort of the educational process. So, well, I could talk about all kinds of things. I could talk a bit about, sort of the implications of some of what I'm dealing with for kind of AI, the future of society. We talk about mathematics, the future of pure mathematics, things like that. It's lots of, but maybe instead of me going through all of these topics, maybe I can, maybe I should finish here and turn this over to questions and discussion. So what I've tried to give you is some sort of glimpse of this kind of layer of computational intelligence that we've been building. I've been building for the last 40 years about, intensely for the last 32 years. I was very, very pleased that we just had the 30th anniversary of Mathematica on June 23rd of this year, and I was able to get a version 1 of Mathematica running on an old Mac computer, and that was fine and good. But the thing that really was exciting to me was I made a notebook in version 1 on this very old Mac computer. I put it on a floppy disk. I read the floppy disk onto a modern computer, and then took that version 1 Mathematica notebook, and it just worked, and the code just ran. So over this course of 30 years, one hasn't lost anything. So that means that's a very encouraging thing for the future as people write these kind of computational essays to explain explain things and so on, and it contains code and such like. That code can be expected to keep working forever. And I can talk other topics we maybe talk about are things about sort of what's involved in this process of designing a language. It's kind of I think designing languages is something that's an underappreciated activity, because the fact is, if you design a language well, it provides a framework for people to think about things in, and it's sort of a lot of effort to kind of polish ideas to the point where you can have a clean and coherent design for language. But once you have it, it provides a great framework for people to think about things. I know that actually at this university, you guys have a site license for all of our technology. So anybody here who wants to use any of this stuff, do more things with it,
since we are recording, that you please ask the question on the microphone so that the video captures your question, otherwise you don't know. But the question here, so I'm going to jump down.
Hi, good afternoon. Thank you for the presentation. About how you start your company, how was the beginning when you first, how do you think and how do you do to protect your idea and to start your company? Okay. How you do that?
So, it's a bit of a long story, but I'll try and tell it. So, I started off, as was mentioned at the beginning, I started off as doing physics, and I got involved in physics when I was a teenager, actually. It was the sort of golden age of particle physics. Kind of neat, because it's like today it's the golden age of machine learning. And, you know, if you're in a field during its golden age, the things you do tend to live forever, because the field, so, you know, the things I did when I was a teenager, people are still using, I think, particle physics. One of the things that happened, I was really interested in physics, but I didn't really like doing kind of the mechanical, mathematical calculations that you end up having to do in physics. And I was like, there's got to be a better way to do this. And I realized computers were a better way to do it. And so I started using computers to do mathematical calculations and so on. And there were some systems that had been built for research purposes and so on for doing that. And I quickly became the world's largest user of these things. It always amazed me that nobody else used this stuff. I mean, admittedly, they were research systems and they required a lot of babysitting. But still, they existed, and you know, I quickly became, you know, in the ranking of physicists who could do integrals and things like that. I was a really top one, but it wasn't me. It was just the computer doing it for me. Although, by doing many, many integrals by computer, I got a lot of intuition about how, you know, like that integral that showed up earlier where it involved a trilogarithm function. If I'd thought about that a little bit more, I probably would have been able to guess that it would involve a trilogarithm function, which is because I've seen a lot of integrals that are a little bit out of practice. But anyway, so I did that, and in 1979, which was when I got my PhD, and I was 20 years old at that point, and I had kind of, the systems that existed, the research systems that existed, basically, I had maxed them out. I mean, the things I wanted to do, they couldn't do anymore. So I was like, what am I going to do next? So the answer is, I have to build it. You know, I tried to convince the people who built these existing systems to build a version 2.0. That didn't work. So then I thought, okay, well, I'm going to build it myself. So that was 1979. I remember I was at Caltech at that time, and I went to the bookstore, and I just bought sort of all the books about computer science that existed, about that large number of books. And I spent a weekend reading them all, and learning I knew a lot of stuff already, but that was kind of, you know, making sure I kind of knew the existing corpus of knowledge about computer science at that time, and then started building a system initially to do kind of mathematical computation. But the idea, I kind of thought I wanted sort of dig down to make the system based on as fundamental principles as possible. That ended up being a big adventure in understanding mathematical logic and the whole history of formalization and so on. And I built the system, it's called SMP, and it was a system for doing symbolic manipulation and so on. And that got finished around 1981. Then the problem was, what was I going to do with it? Because it was a pretty big system that had been built, and it was very practical, and it was clear that lots of people could use it. I mean, I built it sort of because I wanted to use it, but it was a big project, and it was something where lots of other people could use it. And so I thought, well, what am I going to do with this? And I realized that the only way that was practical forward was to start a company around it. There's a bit of complexity because I initially was like, let me license this through the university, but the university didn't know what to do with it, and then later on the university decided that it really would have liked to do something with it. It was kind of too late by that time, so that made a big mess. But basically then I started my first company. I guess I was 21 years old maybe, and I at the time I was basically thought of myself as a young physics professor, and what do I know about starting companies? And so I found a bunch of business people, and I hired a CEO, and we got a bunch of venture capital. usual, what today will be the usual thing. In those days, that was a long time ago, so the whole ecosystem of venture capital and so on didn't really exist at that time. All the venture capitalists were in New York, they weren't any in Silicon Valley. So that company, the main thing I learned from that company was that I wasn't as bad at business as I thought I might be. Because what happened was, the people that I brought in, I kept on being like, I think we should do this. And they would say, no, I think we should do the opposite. And it would turn out I was right and they were wrong. So that was, I didn't really have a self-image that I knew much about business, but it seemed like common sense, took me in the right direction. So anyway, that company eventually kind of had a bunch of adventures, but eventually the company actually went public sometime in the 1990s, although it had kind of gone off into different directions by that time. But I fairly quickly, peeled off from that company because I wasn't happy with what it was doing. Then I spent a few years working on basic science mostly, but as a hobby I did strategy consulting for tech companies. So I saw many things. That was kind of I saw many stupid things be done. It was, so then in 1986, I had been building up this kind of direction in science that came out of my work in cellular automata and so on. And I had started, I went round to different universities around the US and I said, where am I going to start a big research center for this kind of science? And the university that won was the University of Illinois. So I went there and I very quickly realized that running a research center at a university was not a good match with my personal, capabilities. And so I thought, what is plan B for moving the science ahead? Rather than getting a lot of other people to work on this science, I decided plan B is I'll build the best tools I can, and I'll build an environment where I can just work on ideas and going forward. And so I started my company, Wolfram Research, in 1986, and I've been running it ever since. Now, the second time round, I made many fewer mistakes than the first time round. I mean, I don't have any outside investors in my company. The company is about 800 people these days, and it's about very geographically distributed, actually. I think the main companies develop, they develop a certain internal culture, and our company is very much oriented towards producing, innovative R&D and delivering it as practical products. The company is is really, of those 800 people, the vast majority are R&D people. The commercial side of the operation is very small, actually embarrassingly small. We're lucky enough that the products kind of sell themselves and we don't really have competition, and so that keeps my life kind of simple. But actually one thing I might show you that's been kind of fun. So one of the big things that I spend time doing is trying to design our technology and the strategy of what we do with it. And so I have kind of a process for doing this, and one of the things that I decided is it's quite the process of doing this kind of design, system design and so on, is kind of interesting, and it's a big mixture of very theoretical, philosophical kinds of things with very practical, pragmatic software engineering kinds of things. And it's, we have a great team of people, and we always have interesting discussions, and they're very fast-moving things, trying to design things. And I thought maybe other people out there in the world would think it was fun to listen to this stuff going on. So about sometime at the end of last year, I started live streaming a bunch of our internal design meetings. And we've done about 120 of them or something now that are live streamed. It's hundreds and hundreds of hours of the design of different kinds of features in Wolfram language. It's actually been very, very interesting because a lot of sophisticated users of ours kind of tune into these live streams and make real-time comments and so on, which is quite an interesting process. But anyway, so if you're curious what's actually involved in the front lines of building all this stuff, you can sample some of these things.
Okay, let's move to the next question here. And I have something. Se você quiser perguntar em português, eu traduzo se precisar para os alunos. I can translate for the students so that they are shy.
Ok, Okay, thank you for your talk. I noticed when you were coding that you're using the percentage sign to recall a past line. And I was wondering if you were keeping the past results in memory or if you're just recalculating it. And if you're keeping them in memory, is it somehow vulnerable to some sort of overflow?
Some sort of what?
Overflow in the memory.
Yeah, so I mean the way it works is if you look at the prompts on the side here, it says out 75 equals. That means it's assigning that object out 75 to that output. So it's in 75 colon equals means it's doing a delayed assignment of that input. So if I reevaluate that, it will redo the computation. So yes, the things that I have here are basically kept in memory. You can delete them. You just say, just clear, for example, out, and it will clear all the things from memory. But that really, honestly, in the modern world is not a problem. It's not a problem on the desktop computer, it's not a problem in the cloud. By the time you can display it, you can store it in memory. Now, it's a little bit, there are cases where, for some things like, I don't know, audio streams and things, there's a whole much more elaborate system where it's caching things in files and so on because it doesn't make sense to have it in directly in memory. So, yeah.
Good afternoon. I have a question. Isn't the very notion of universal language incompatible with things like Gödel's incompleteness theorem and Tarski's semantic conception of truth?
Okay, right. So there's certainly no inconsistency. So what does it mean to have a universal language? So there's different levels of what that might mean. One is a way to represent human thoughts in precise symbolic form. That's one goal, is to have a language independent of the details of English or Portuguese or whatever, to have a sort of symbolic representation. That really isn't very connected to questions like Gödel's theorem. The kinds of things that are much more connected. So let me show you something. So let's take our friendly Rule 110 cellular automaton and say, okay. So if you can see this, this is just starting the Rule 110 cellular automaton off from a single cell initial condition. And it happens to grow only on one side, but you see all those little structures that it produces. So the question is, what's going to happen in the end? Are those structures going to survive forever, or are they eventually going to die out? And it turns out that, in general, that to know the answer to that question, you have to sort of keep running the system and see what happens. But if you want to ask the question, what can ever happen, even after an infinite time, it might take you an infinite amount of computation to work that out. And that's an example of something where there's undecidability in the same sense as in Gödel's theorem. The thing that this is kind of analogous to the Holton problem for Turing machines, which is connected into all of those kinds of things. Now, to address, okay, I'm trying to interpolate different possible meanings to your question, but so there's another issue, which is in Gödel's theorem. So you might think that if you want to say things about integers and about arithmetic, that you could write down axioms that would describe integers and nothing but integers. So you could say, a plus b equals b plus a, etc., etc., etc. Have a bunch of axioms. You have some finite set of axioms. You might say those axioms will be consistent with arithmetic, with integers and nothing but integers. But one of the consequences of Gödel's theorem is that any finite set of axioms, if you write them down, they can't constrain you to be just talking about integers and nothing but integers. You'll have these non-standard arithmetics and all kinds of weird things that, and there's no finite set of axioms that guarantee to give you just the integers and nothing but the integers. So that has some interesting consequences because that phenomenon of kind of not being able to constrain what you're talking about precisely with a finite set of axioms is something which has implications for things like, I don't know, things like AI ethics, trying to describe, because what you're trying to do is you're trying to say, I want the AIs to behave in this way and I never want anything weird to happen. And it turns out that there just isn't a finite set of laws, effectively, that you can ever give that will constrain the AIs to sort of just do whatever it is that you wanted them to do and not have any sort of unexpected consequences. So that's a sense in which Gödel's theorem shows that, you know, when people say, let's just write down the 3 laws of robotics and that will determine how AIs will work, nothing like that can possibly work. And that's sort of a consequence of things like Gödel's theorem. But so there's lots to say about this. I mean, in terms of the way all this stuff plays out in mathematics, one of the big mysteries for me about mathematics is that it's possible. By which I mean that, you know, it might be the case that most questions you ask in mathematics are undecidable or unprovable. The fact that most mathematics has turned out to be doable, at least the mathematics people have chosen to do has been doable, I think is in some sense surprising. So for example, when we try and solve equations involving integers, Diophantine equations, like, you know, Fermat's last theorem type equations, it's known that for sufficiently complicated such equations that it is undecidable whether the equation has solutions or not. The question is, does that happen to sort of naturally occurring equations, or do you have to go to these specially constructed equations? My guess is, from what I've seen from the principle of computational equivalence and so on, that this kind of phenomenon happens even in quite simple equations. And in fact, many of the unsolved problems of math may turn out to be actually undecidable based on the axioms that we have in mathematics. So, long answer to perhaps what you were asking.
Thank you, Wolfram. Tell more about the artificial intelligence and the future of humanity and the universe with this idea of artificial intelligence and the connection of people and computer. Computer understand our mind, and imagine your system connecting with our mental states and the emotions.
So wait a minute, I heard the end of that question, but I didn't understand the beginning. Could you repeat the beginning?
Tell more about your idea of the future of artificial intelligence, the importance of artificial intelligence, and the connection of our mind and systems, saying your system.
So one question is, does, you know, my goal with Wolfram language is to connect the kinds of things that we think about with the kinds of things that computers can do. The way that it is not I'm not so concerned with understanding how our mind works and seeing how that corresponds to how the computer works. I mean, we know, for example, in the case of an image identification neural network, we know that the first few layers of the neural network pick out features that are very similar to the features that are picked out by the first few levels of the visual cortex. You know, I don't. The question of, you know, I'm mostly interested in the building of technology for these things, not. I mean, it's kind of like if you're trying to make things that fly, you can build airplanes, or you can try and understand bird flight. And I'm more in the building airplanes mode. So I don't expect. I mean, there's a question of how we interact with the kind of AI that we're building and what the role of so I think the way I see it is that we humans have to define the goals that we're trying to achieve, and then it's up to our systems to automate the process of getting to those goals. And that's
So we have a couple more questions here.
yeah.
Good afternoon. Yeah, my question is about the computing equivalence principle you talked about. So, when you spoke, you said no computing, you can't, how can I say, you can't save computing to predict things because there are certain equivalence principle. But when you talk, you're talking about complete certain sets of objects. You know the complete information about the states of the objects, and you want to know everything about them. But human experience is not that. We work under uncertainty, and our most recent founds in physics corroborates that uncertainty is a fundamental aspect of our universe. So I want to know if you think the computer equivalence principle you've talked about holds under abstraction and uncertainty. And if not, if somehow it relates with your research in automation and Cohen's game of life or surreal numbers.
Right. Okay, that's a bunch of different things. So first issue is the systems that I'm looking at are, as you say, deterministic systems. You have precise rules, you're looking for precise outputs. You can also say, just tell me statistically what happens in the system. Does the system have more zeros than ones? Does the system whatever? Turns out computational reducibility applies to those statistical statements just as well as it applies to precise statements. Some things, like in Rule 30, the fact that there are roughly equal number of zeros and ones in the center column, that can be easy to work out. But if you look at different statistical characteristics, you have exactly the same problem. You don't escape computational reducibility by just trying to sort of smooth things out with statistics. That doesn't seem like that doesn't turn out to work. You can, as a matter of fact, you can start thinking about, you can make things very difficult for yourself by thinking about probability distributions and how you evolve the probability distributions. That's actually tends to be more complicated. Actually, you can do very nice things in Wolfram language with probability distributions and manipulating probability distributions. So you don't escape computational reducibility by using statistical type methods. Now, let's see, in terms of, in physics, the people sort of imagine that there's, well, a couple of things. So we don't know whether the universe fundamentally uses real numbers or fundamentally uses integers. I don't know of any real evidence that the universe fundamentally uses real numbers, and it's simpler, at least for us, to think about in terms of discrete dynamics. And so that's the place to start. It may turn out that the theory of physics, there is no theory of physics based on discrete programs, in which case we'll have to try, plan B. But to start with, that's, I think, a good working hypothesis. I mean, I think it is a quirk of history that we believe that space-time is continuous. I think that, when back in the 1920s, when people were, first studying quantum mechanics, it seemed like everything was quantized. Angular momentum is quantized. The position, momentum, their quantization of those things. Fields are quantized. And people at first assumed that space and time will be quantized, but then they found inconsistencies with special relativity and so on, and they just gave up. Actually, Einstein, in his later years, somebody recently gave me this kind of quote, said, I'm pretty sure that in the end space and time will turn out to be discrete, but we don't yet have the mathematical apparatus that we need to be able to analyze that. We've had this issue of sort of apparent incompatibility. There actually isn't in these network models that I have. There isn't incompatibility with either special relativity or even general relativity. So that problem doesn't really arise there. Now, the question of quantum mechanics is a whole other can of worms. One of the issues of quantum mechanics is knowing, what is the essence of quantum mechanics? What is the phenomenon which, if you see it, you know you have quantum mechanics? It's extremely slippery. It's even slipperier in quantum field theory than it is in quantum mechanics. And we can see in some of these network models little indications of things that are quantum-like phenomena. But knowing that, yes, I've really got quantum mechanics, there isn't a good way to do that. And I think, when you talk about quantum computers, for example, that's a whole other kind of can of worms. I mean, I worked on quantum computers back in 1980, actually, and particularly around 84, 85. I guess Dick Feynman, well-known physicist, and I were both he and I were consultants at a parallel computer company in Boston. uses quantum mechanics to produce perfect randomness. And it was an interesting process to think about that, because in the end, we realized that's actually a lot harder than it seems, because you measure one quantum bit, you have to amplify it, and to make it something that is a definite measurement. That amplification process produces all kinds of gunk. If you try and measure the next bit, you haven't cleaned out that gunk before the next bit comes in. So anyway, there's a whole kind of. So I'm a bit skeptical about quantum computers. We've been, people have used Wolfram language to simulate quantum computers for years, and we even have a nice little package that we've been developing for doing quantum computer simulations. We've been keen to connect that actually to the to actual quantum computers, and somehow every time the companies that have tried to make quantum computers have been very keen for us to do that connection. Well, until it comes to the point where we're actually doing the connection, because I think everybody knows that as soon as we actually make that connection, within a very short amount of time, we're going to know whether these quantum computers work or not. But so I can't yet tell you that we've made a connection and we've seen them work, which kind of tells you something, right? Yes.
Recently, I read an article, I think it was in The Atlantic, but it talked about how the scientific article is changing. It's incorporating more interactive elements and also showing the computations. And it talked about Mathematica notebooks and also open source alternatives. And the article seemed a bit biased against Mathematica because the author was afraid that people might get locked into a certain company or a certain product that other people might not be able to have. So I would like to know your thoughts on this, on open source versus closed source software.
Right. So I mean, these are two different business models, right? In, our model has been, we try and, we sort of put a lot of effort into making the best products we can in an organized kind of, in a way where I'm providing leadership, we have a whole team of people, it's a very systematic thing. People, lots of people have worked on these products for 25 years, et cetera, et cetera, et cetera. It's a very systematic kind of thing. And my goal is to align the value that people get from using the products with, how we support this effort should be aligned with the value that people get from using the products. And so we have a pretty simple sort of ecosystem for doing that, where now we've done, like Wolfram Alpha is free. So that's an example of something we just give it away to the world. It's more than open source. It's just a free thing where we're paying for the servers and people just get to use it. In terms of Wolfram language, one of the great things is that the code is very open, because people can take fragments of code, they can use it elsewhere. We've had this thing called our demonstrations project. There's about 11,000 contributed demonstrations where people can take the code from that and use it elsewhere. So the thing we've been, it's interesting because sort of software licensing is evolving, and we're trying to do something where we maintain the ability to have kind of consistent leadership and consistent development. And I'm sort of proud of the fact that for 30 years we've had kind of a compatible product and so on. I think that what's tended to happen with open source, like I noticed, the chap who did Python just quit the whole Python effort out of kind of disgust because he couldn't manage the kind of dynamics of open source. So that's kind of an example of the bad case scenario, so to speak. I think that open source is good when you don't have to figure all the stuff out, when you can copy something that already exists. If you have to figure new stuff out, you need leadership, and that's hard to get in that kind of environment. You also ultimately need things where I mean, there's some, in the end, I mean, one of the weird things about open source is, you think it's free, but it actually isn't. Because it turns out, the worst case, which has become very common, is open source has become kind of a brand. And companies will say, oh, our CRM system is open source. It turns out, if you actually want to use that system in any real way, you pay a lot of money for it. Sometimes more than you would pay for an actual, we're just going to sell you the system and it's going to work. actually really annoys me because we've ended up being bitten by that several times at our company. You know, and then there are these different models. Well, you know, you can pay for maintenance, you can do this, you can do that. What we've been trying to do is to make our system, I mean, my goal is pretty simple. My goal is to get the things we've built to be as widely used as possible. And also to be able to keep developing them and keep kind of consistently innovating. So, you know, what's the optimal way to do that? We've got a bunch of different models. So one thing that's actually just happening is that we have a thing called our notebook archive, which is part of our foundation. And the way it will work is that anybody can publish a notebook into this notebook archive. We're going to guarantee that that notebook will keep running forever. Not just that the code will be there, but the thing will actually run on servers forever. So that's a thing where, in terms of, for example, you know, publishing material, that's something where this, I think, is a really good solution because people can take, you know, the notebooks they've written, they can put them in the notebook archive, it'll keep running. The way it works is it's free for anybody to use the notebooks in the notebook archive. If they want to edit those notebooks for themselves, they can do a certain amount of that for free. If they really want to do serious production work, then they actually, you know, pay for a subscription and they go on. Now, the other thing worth saying is that in practice, our products are free to most people in academic and educational settings because most major universities around the world have site licenses for our products. So that's and you know, we've done particular things like on the Raspberry Pi computer, we've bundled Wolfram language as a free feature of Raspberry Pi. But so, you know, the thing that I've thought about quite a lot actually is how do you navigate, you know, given the value that people get from what we do, given, you know, what it costs to do the R&D to make it, and sort of the expectations that people have, how do you manage all of those things and come out with something where as many people as possible can make use of the things we've tried to build. And I'm not sure we've got the perfect solution, but we think we have a pretty good solution. And I think so yeah, that's probably more to say about this topic. I mean, there's some other things to say that have to do with, for software developers, there's a bunch of stuff to do with versions of Wolfram language that are embedded inside other IDEs that are actually going to be free things that you can embed inside other IDEs and use for development freely. And when you want a production license that has an SLA and so on, then you end up paying for that, but when it's in the development phase, you're not. There's a bunch of other details of these things, which are, but it's interesting because, you know, our overall goal is just get as many people to use this technology as possible, because I just spent 32 years developing the thing, and, you know, I'd like to see people actually use it. I suppose one thing that's happened in the software industry is that many, you know, when you look at some categories of software, frankly, they're way too expensive. And companies have found that, you know, they've got people where they've made use of that software and they gradually, you know, they increase the prices to the point where it seems very usurious. I have to say that we have never done that. If you look at our prices, they've basically been constant for 30 years. So, you know, I think that we are somewhat the sort of the thing like, oh, I want something open source is sort of partly a reaction to the fact that people have done very unreasonable things with software pricing, which we have not done. And you know, and it's also the case that unfortunately with you know, the bad thing with open source is not only you end up with these things that are supposedly open source, but then they're not. You end up with these things where, oh well, it's open source, but there are patents that you have to license. Well, then there's, you know, there's a lot of other weird squiggly things that go on. And I prefer the model that we've adopted, which is just very simple. And that's, it seems to work well.
So, we're not completely done yet, but we're running a little bit late. So I have only 2 more questions, but I would like to make an announcement that at 5 p.m. there will be a Q&A with Stephen and the physics students in 1 hour. So if you have more questions, I I was told that you can show up there and ask more questions there, so you can, keep your questions. So let's do one or two more questions depending on how long they are.
So the database that you created, like the knowledge base, is almost obviously revolutionary, and the whole amount of computations you can do on top of it are incredible. But you still, as you said yourself, you have to curate it. You have to say that that is true. So you're kind of limited into a consensus knowledge base. How can you? Is it possible, or which would be the steps that you would take, or we would take as humanity, to circumvent the curator, or into flipping your system around, and instead of bringing the truth and taking processes and information out of computations of it, you could just give it data and ask, is it true or not? How can you flood it with information and talk about truth? So you could do fact checking or even policy making with it.
Right. Yeah, it always I run into people who are policymakers and they say, oh, I looked up such and such a thing in Wolfram Alpha and therefore I decided to do such and such a policy thing, which always makes me a little bit nervous.
Yeah, sure.
No, I mean, first thing is that obviously there are lots of ways to flow data from the world into our system. So there's a thing we call our data drop, which is a thing where you can take data from things like IoT devices and so on. So in any case, so first thing is you can obviously flow data into the system. Now, in terms of I mean, in a sense, we do a huge amount of fact checking when we are curating data, and we are, I think it's fair to say, definitively the number one reporters of data errors to the upstream data providers that we use, because we're able to cross-check lots of different kinds of data. Now, another question is, another question is, deciding what's true. So one of the areas that we've been much involved with recently is computational contracts, kind of a generalization of smart contracts on blockchains and so on. And the thing you typically want there is, somebody pays somebody if something happens in the world. Okay, so you have to know, did it really happen? And sometimes that's pretty straightforward. Did it rain somewhere? Well, probably the sensor that measures that, probably okay. Did somebody walk 10,000 steps today? Well, that depends on the little pedometer that's in their pocket, and maybe they did something crazy to that pedometer, and they faked the data. So what we have to do there, for example, is to try and both use anomaly detection with machine learning and also try and make models of the world so we can validate that that data was plausibly correct, or we can cross-check it against other data and so on. So we've actually got quite a emerging big project in trying to create kind of a smart oracle for computational contracts for doing this kind of thing. Now, the next question is, there are matters of judgment. Like, you can say, well, there are kind of almost silly questions like, who's the best actress this year? Okay? That kind of question, who knows how you answer that question? But there is an objective fact that somebody won the Academy Award for Best Actress. And so you can take some of these subjective things and turn them into a concrete version of that. But there's another case, which comes up in computational contracts, which is things might happen in the world where, okay, somebody says, did that house burn down or not? Right? Well, in most countries, in most places, there will be some official record. The fire department will eventually say, okay, that house burned down. But there are situations like, for example, the outcome of elections. So people might say they might have some contract that says, or might be using a prediction market to kind of bet on the outcome of an election. You say, well, it's obvious, which way the election goes. Well, it might not be obvious. There might be some big complicated mess that develops where you don't even know when it's over, and there's a question of how do you do the curation? Because when you have a computational contract where there's millions of dollars of people betting on either side of the thing, at some point those people were basically made contracts with each other saying, we will choose to resolve our bets based on what what we, for example, decide is the correct thing. So we've been thinking quite a bit about how to deal with situations like that. And my basic principle about it is we have to set up a system where we can be wrong, but we can't be dishonest. So in other words, we'll have some criterion and we'll do the best we can, and maybe it will turn out we were wrong, but we can't be affected by the fact that we can't have sort of insider trading of people betting themselves on what the outcome is and so on. So we've started, we haven't got there yet. We've started trying to design systems that will basically, for example, even using live streaming is one thing. It's like, okay, you have 5 curators who are randomly picked from a pool of 200. At the moment we have to make the decision, every one of them, everything they do is live streamed, and they have 15 minutes to decide what the outcome is. So that's an example of a kind of, just a management process for dealing with that. But it's a really interesting question, how one resolves those kinds of things. And it's important for doing computational contracts, etc.
Okay, I'm happy that we have many more questions, but we have to thank Stephen again now at the moment. Those interested are invited to come to the student discussion session 5 p.m. at the Physics building, 3rd floor, 327, room 327, okay, at 5.